All right, we are going to go over the chapter 5 problem set. So, for the first problem, you're supposed to describe each of these molecules as being chiral or achiral. And if you decide that the molecule is achiral, then you need to decide if it's achiral because it has no chiral centers, or if it's achiral because it's meso, meaning that there are two or more chiral centers and a plane of symmetry. So hopefully as we go through this, you'll feel very confident in answering these types of questions. So for letter A, hopefully as we look at letter A, we can realize that there are two chiral centers. There are two centers with four different things attached. What you might be wondering is if there technically is a plane of symmetry down the middle of the molecule. But because when we fold over the molecule, one methyl is up and one methyl is down, they do not perfectly fold on top of each other. And so therefore, letter A is simply a chiral molecule, meaning that its mirror image is the opposite and not the same as the original. Letter B, as we look at letter B, we should recognize that there are two chiral centers, one here and one here. Because this molecule is linear, it doesn't look like it's meso, but linear molecules sometimes do not look meso even though they are. It's just basically how they're drawn that causes them not to look symmetrical. So when you have a linear molecule and both chiral centers have the same four groups attached like here, so what I mean is this is a chlorine, this is a chlorine, methyl, methyl, CH2, CH2, and then technically both of these have a hydrogen attached to them. So because we have two chiral centers with the same four groups attached and a possible plane of symmetry down the middle here, the easiest way to determine if it's meso is to determine R or S at each chiral center. So I'm not going to go through this like in detail determining R or S because we will go through that. I think it's on problem 3, but we will still just go over this quickly. So chlorine is 1, this group is 2, this group is 3, hydrogen is in the back, it's 4. So 1 to 2 to 3, and the hydrogen's in the back. This is going to be R. And over here, chlorine is 1, the group in the middle is 2, this is 3, and the hydrogen's 4. So it looks R, but since the hydrogen's in the front, we had to switch it. It's going to be S. So we have two chiral centers that have the same groups attached, and one side is R and one side is S. This means that this molecule is going to be achiral because it is meso. The mirror image of B will have one R and one S, and it will be identical to letter B. Letter C, we hopefully recognize that there are two chiral centers. The first question that you should be in the habit of asking yourself is there a chiral center? So just to confirm that to ourselves, we have a chlorine and a hydrogen, a CH2, and then a CH. And then on the other side, we have a CH3 and a hydrogen and a CH2 and a CH. So we have 4 different groups attached to each of those centers, and we do not have a plane of symmetry down the middle because we have a chlorine on one side and a methyl on the other. If this was chlorine, then we'd have a meso compound. But because one's chlorine and one's CH3, this molecule is simply a chiral molecule. Letter D, we have two chiral centers, and hopefully we realize that the same 4 groups are attached to them. Bromine, bromine, methyl, methyl, CH2, CH2, and then they both have a hydrogen. So because this is linear and it's not an obvious plane of symmetry, the best thing to do is determine R or S. So bromine is 1, the group in the middle is 2, this group is 3, and the hydrogen is 4. So this one is going clockwise, and the hydrogen's in the back, so it is what it is. This is going to be R. And then on the other side, 1, 2, 3, and hydrogen is 4. So it is going clockwise and hydrogen's in the back. It is what it is. This is also going to be R. So because this molecule is RR, it means that an enantiomer exists of it, SS. So this molecule is simply chiral. Letter E looks similar to D. We have two chiral centers, but this one has an obvious plane of symmetry. If you draw a line down the middle of the molecule, both sides perfectly are symmetrical with each other. So this molecule is achiral because it is meso. If you want to figure out R or S, one side should be R and the other should be S. Letter F looks similar to E and D. So we have two chiral centers. We do not have an obvious plane of symmetry. So the best thing to do is determine R or S. So we're going to go 1, 2, 3, and hydrogen is in the back. It is 4. So this one is going clockwise. It's going to be R. And then bromine is 1. The group in the middle is 2. This group is 3. But our hydrogen is in the front. That is 4. So it looks like it's going to be S, but we have to switch it because the hydrogen's in the front. It's going to be R, which technically means it's identical to D, even though they do not look that way. So this is a chiral molecule. Letter G. We might look at letter G and instinctively think that there is a chiral center, but as we look at the carbon I circled in red here, we have a CH3. We technically have a hydrogen in the back, and then we have a CH2 and a CH2. So since it's a tie, we had to look out one further. And so down here we'd say CH2 versus CH2, which is technically a tie. So we go one further and they meet. So because there is not 4 different things attached there, it is not a chiral center, which simply makes this molecule achiral. Letter H, you might instinctively think there are 2 chiral centers, but let's take a closer look. We have a CH3 here. It has also a hydrogen. And then we look CH2 versus CH2. It's a tie. So we go one further. CH2 versus CH2. It's a tie. And then they meet up. So there are not 4 different things attached to either of those places that look like chiral centers. So this molecule is simply achiral. Letter I. We hopefully look at letter I and say there are 2 chiral centers. We have chlorine, chlorine. We have methyl, methyl. They each have a hydrogen. And then they have a CH2 in the middle. So we have 2 chiral centers with the same 4 groups attached. Again, the molecule is linear, and so we have to be asking ourselves, is this a meso compound? Is there a plane of symmetry that's not obvious? So easiest way to solve this is to determine R or S. So chlorine is 1, this group is 2, this is 3, and our hydrogen's 4. So this is going to be, it looks R, but since the hydrogen's in the front, we'll switch it. It'll be S. And then on the other side, chlorine is 1, this group is 2, this is 3, hydrogen's in the back, it's 4. So because the hydrogen's in the back, it is what it is. This is going to be R. So since one side is S and the other side is R, this is going to be an achiral molecule because it is meso. Letter J, we have the same kind of thing. Chlorine, chlorine, methyl, methyl, hydrogen, hydrogen, CH2, CH2. So because we have a possible plane of symmetry, we're going to determine R or S. Just for clarification, this is not an obvious plane of symmetry because the chlorine's up on one end and down on the other. So you can't just look at it and say it's meso. So let's determine R or S. On the left side, chlorine is 1, this group is 2, this is 3, hydrogen's in the back, it's 4. So this is going clockwise. It's going to be R. And then on the other side, chlorine is 1, this group is 2, this group is 3, and hydrogen is in the back, it's 4. So this one is also going to be R. So since it's RR, this is going to be a chiral molecule. Letter K, we might instinctively think there are 2 chiral centers, but as we look through that molecule, we'd say this group has a CH3, it has a hydrogen, and this group has CH2 versus CH2. We go one further and they meet up, which means that there is not 4 different things attached to that center. Same thing goes for the top chiral center. So this is an achiral molecule because there are no chiral centers. Letter L, hopefully we recognize that there are 2 chiral centers. It has a CH3, an H, a CH2 versus a CH2, and then when you go out one further, they are different. So we have 2 chiral centers there, and so then we have to ask, does it have an obvious plane of symmetry? So if we put a line down the middle of the molecule this way, it does. Both of our chiral centers have the same things attached. So this molecule is achiral because it's meso. And again, if you wanted to figure out R or S, you'd find one side's R and the other is S in letter L. Letter M, hopefully we see this as a possible chiral center. It's got a CH3, it's got an H, a carbon with a double bond, and then a CH2. So we have 4 different things attached. So it's got 1 chiral center, and you don't worry about it being meso since there's only 1 chiral center. So this molecule is simply chiral. Letter N, we have 2 possible chiral centers. Let's just confirm they're chiral. So CH3, H, CH2, and then a carbon with a double bond. So we do have 2 chiral centers. And then we ask, is there an obvious plane of symmetry? And in this case, the cyclic molecules usually make it more obvious. There is a plane of symmetry down the middle. So this molecule is simply achiral because it is meso. Letter O is tricky. You might think there are 3 chiral centers, but let's go through each one. So starting here, we have a CH3, we have an H, we have a CH2, and then we have a CH over here. So we have 4 different groups attached, which means that this is a chiral center. Let's go to the bottom right one. So we have CH3H, and then we have a CH with a methyl, and we have a CH with a methyl. So these 2 groups are the same. So we go one further, and they meet up. So that bottom right center is not chiral. So this one is not a chiral center. Well, this one was. And so as we look at the last one up here, it goes CH3, H, we have a CH, CH3, and a CH2. So this one is also chiral. So we have 2 chiral centers. So then we have to ask, is there a plane of symmetry? So I'm going to erase this on here. And so if you look down this bond, you could think that maybe there's a plane of symmetry, but one methyl is up and one methyl is down. And so this molecule is simply chiral. It has 2 chiral centers, but not a plane of symmetry. And the last one, letter D, hopefully we recognize we have 2 chiral centers and a possible plane of symmetry here. So we have OH, OH, CH3, CH3. We have hydrogen, hydrogen, and then they meet in the middle. So To definitively determine if it's meso, we'll figure out R or S. So the left side, it goes 1, 2, 3, 4. So this looks to be R. And the hydrogen is in the back, so it is what it is. And the other side, 1, 2, 3. And the hydrogen is in the front, so we'll have to switch it. It looks R, but we switch it, it'll be S. So because one side is R and one side is S, this compound is going to be achiral because it is meso. So for the last part of this problem, it asks which of the above compounds are optically active. So remember, that means that they rotate light. So the only compounds that rotate light are chiral molecules. So we're going to go through this and identify all the chiral molecules we showed above. Okay, so above, we'll use the highlighter here. So we're looking for all the chiral molecules. So we'll say A is chiral, C is chiral, D is chiral, F is chiral. So A, C, D, F. And then from below here, we have J, M, and O. So those are all going to be compounds that rotate light, and that is all because they are chiral. All right, on problem 2, we are supposed to determine the relationship between each of the following pairs of molecules. So we're going to classify them as constitutional isomers, enantiomers, diastereomers, or identical. So just a quick recap. A constitutional isomer means the same molecular formula but arranged differently. So here is an example of a constitutional isomer, cyclohexane versus methylcyclopentane. Enantiomers means they are opposite. So if one molecule is R, the enantiomer of it would be S. Diastereomers means there are two or more chiral centers. So if one molecule is RR, the other would be RS. So they're always the same at one site and then opposite at the other. And then identical just means they're the same. So there are a few ways you can think about each of these. If you're a more visual person, you are welcome to try to rotate it mentally in your head. If you're not so visual, the best way is to determine R or S. So let's just look at A. So as we look at A, if we're going to try to think about this like visually, for A, if we take this molecule here and rotate it like a steering wheel, okay? So we're going to take our steering wheel like this, and we are going to turn it this way. So when we do that, if we turn it so that this molecule, this methyl group that was down is now 2 positions counterclockwise, then the methyl that was going up would be positioned this way. So again, all I've done is taken this molecule and turned it this way. And so if we do that, when we compare these two molecules, hopefully we can realize that they look like mirror images of each other. So because they would be mirror images, the relationship between them should be enantiomers. Now, you kind of have to take that with a grain of salt. If you're very visual, then it's best to also try to like flip one of the molecules and get it to superimpose on the other. So with this second molecule that we've drawn, there's no way to flip it so that it exactly lines up with the original molecule. It always looks like the enantiomer. If you're ever in doubt, just figure out the chirality, like figure out R or S. So we can quickly do that. So for this first chiral center, it would go 1, 2, 3, and the hydrogen is in the back. It's 4. So this is going to be R. And then for the other one, this is 1, this is 2, this is 3, and the hydrogen's in the front. It's 4. So it looks to be S, but since the hydrogen's in the front, it's going to be R. And then over on the other side, we have 1, 2, 3, and hydrogens in the back. So it looks to be S and the hydrogens in the back, so it is what it is. And then for the bottom chiral center, same thing. 1, 2, 3 hydrogens in the front. So 1 to 2 to 3. It looks S. It looks R, but the hydrogen's in the front, so we're going to switch it. It'll be S. So the original molecule, RR, and this one's SS. So they are complete opposites of each other, which is why they are enantiomers. Letter B. Letter B, I think visually, it's a little bit harder to flip it over. If you want to envision the molecule over here like a piece of paper, I would try to get those two double bonds to line up. So if this is the front of the paper, you're going to flip it. So now the back is like take it like a piece of paper and flip it over. So when you do that, if you're a visual person, this double bond would come here, and then your SH would be down. So when you compare the two molecules, the original and this one, you'd say they are different by two groups. The hydrogen and the SH are switched. So anytime you switch any two groups, you switch the chirality, which means that those two molecules must be enantiomers. Again, if you're not a visual person, let's erase this just to clear our mind here for a second, then determine R or S. So you'd say 1, 2, 3, hydrogen is in the back, it's 4. So 1 to 2 to 3, it looks like it's going clockwise, which would make it R. And then over here, 1, 2, 3, and hydrogen's in the back. So it is what it is. It is going to be S. So because one side is R and the other side is S, it confirms that those are indeed enantiomers. Sorry about that. My cat decided to make an appearance. So moving on to C, as we look at these molecules, this is one that you may not need to solve R and S as long as you understand this concept. So for C, we see that the two OHs are anti to each other. They are trans, whereas they are cis on the molecule on the right. So basically this chiral center and this chiral center look exactly the same. So because that skeleton is exactly the same, for example, this would not be exactly the same since one is upside down. We can compare those. So as we said, that first OH, this one and this one are exactly the same, and then this one is opposite. So because it's opposite and one is the same, we should hopefully recognize that these are diastereomers. So again, that would mean they are the same at 1. So these two, they are the same chirality, whereas these two groups are switched, the hydrogen and the OH. Just to give you the full picture, let's determine R or S. So this one goes 1, 2, 3, and the hydrogen is in the back. So this one's going to be R. And then on the other side, 1, 2, 3, and the hydrogen is in the front. So it looks like it's going to be S, but since the hydrogen's in the front, we have to switch it. So it's R. Over here is the same, 1, 2, 3, hydrogen in the back. It would be R, and then 1, 2, 3, hydrogens in the back. This one would be S. So again, R to R, those are identical, and then R to S, those are opposite. So that is why that relationship is diastereomers. Letter D. As we look at letter D, as we're kind of like trying to make this general statement, anytime you switch two groups, like if the group is up and then in the next molecule it's down, and you've just switched like a hydrogen in that group, then you create the enantiomer. So here our CH3 is up, and then we have the hydrogen that's down, whereas over in this other molecule, our hydrogen is up and our CH3 is down. So the only thing that's changed in this relationship is the hydrogen and the CH3. So these two molecules should be enantiomers. And we can confirm that by doing RS. So the double bond is 1, this group is 2, this group is 3, and the hydrogen is 4. So 1 to 2 to 3, this is going to be R, since the hydrogen's in the back. Same over here, 1, 2, 3, but this time the hydrogen's in the front. So even though it looks R, we had to switch it, it's going to be S. So since they're opposite, one's R and one's S, those are going to be enantiomers. And that takes us to this last one. And as you look at this chiral center and this chiral center, you should hopefully notice that the double bond is in a different spot. So as we look here, this one goes CH2 versus carbon with the double bond, and this one goes CH2, CH2. So our connections are different, not just the way it's arranged in space, but the actual connections. So because of that, these are constitutional isomers. Right, for F, we can try to look at these and like visually flip them. So for example, if we took this molecule like a piece of paper and flipped it on this axis, so what we would form, basically we're flipping this over, so our double bond is now going to be here, and then the methyl will be up. So hopefully we can all see that, and then if you compare these two, you would say those two molecules are identical. Again, if visualizing isn't your thing, you're not alone. So if it's not your thing, I would just figure out R or S. So over here we'd say 1, 2, 3, and hydrogen is in the back. It is 4. So it looks like we're going counterclockwise, and the hydrogen is in the back, so it is what it is. It's S. Whereas over here it goes 1, 2, 3. Hydrogen is in the front. So it looks like it's R, but since the hydrogen's in the front, we had to switch it. It will also be S. So those two molecules are identical. Letter G, as we look at these, we're going to take this molecule like a steering wheel. Maybe putting a square around it wasn't my best idea. Let's put a circle around it, or put a circle here. And what we're going to do is turn the steering wheel. So when we turn that molecule, we're going to get it to try to line up with this methyl. So basically we're going to take everything on the ring and move it 2 positions over clockwise. So our methyl would go here, and then moving this 2 spots over, 1, 2, our double bond would go here. So if we turn the molecule like that, we can see that those molecules line up exactly the same, meaning that they should be identical. If visualizing is not your thing, we can again determine R or S. So let's do that. So in the original molecule, the double bond carbon is 1, this is 2, this is 3, and the hydrogen's in the back, it's 4. So it looks like it's going counterclockwise, and the hydrogen, or the lowest priority group, is in the back, so it is what it is. And then on the other one, 1, 2, 3, the hydrogen is in the back, so it goes 1 to 2 to 3. The hydrogen's in the back, so it is what it is. It is also going to be S. So that confirms, but either way works, that they are both, those molecules are identical. So letter H, we have 2 chiral centers. If we try to visually think about this, we could try to visually take this molecule, and I would say you kind of want to flip it over on this axis. So if you're going to try to flip it, you're going to try to get those two bromines to line up. So when you take that molecule, think of it as like flipping our piece of paper over. Since the bromine was down, when you flip it over, the bromine will be up, and then the methyl will be down, and it will look the same as the original molecule, which would mean that these two are identical. Again, if that was not your thing or it doesn't make sense, you could always figure out R or S, or just figure out R and S to confirm your answer. So bromine is 1, this group is 2, this is 3, and the hydrogen's in the back, it's 4. So 1 to 2 to 3, it's going clockwise, it's going to be R. And down below here, this carbon is 1 attached to this chiral center. This is 2, this is 3, and the hydrogen is in the front. It is 4. So 1 to 2 to 3, it's going counterclockwise, but the hydrogen's in the front, so we had to switch it. It's going to be R. And then over on the other chiral center, the bromine is 1, this is 2, this is 3, our hydrogen is in the front, it's 4. So it's going counterclockwise, but we had to switch it because our hydrogen's in the front, it's going to be R. And then on the other chiral center, this group is 1, this is 2, this is 3, and the hydrogen is in the back, it's 4. So we're going clockwise, and the hydrogen's in the back, so it is what it is. This will also be R. So we have come up with RR to RR, which means that they should be identical. Letter I. This one's not as obvious. I guess the way you might think about it is your entire ring here is exactly set up the way that this one is over here. So the main difference that we have is in these groups. So this group is up and this group is down, which means that the hydrogen here is down and the hydrogen here is up. So the only difference in this is the difference of two groups. So as we're trying to reiterate in this explanation, anytime you switch two groups, you switch chirality. So since the two groups are switched, they should be enantiomers of each other. And again, the definitive way is just to determine R or S. So let's go ahead and do that. So in the left molecule, we'd say double bond versus CH2 versus H. So we go out one further, we say double bond versus double bond. And then we'd go one further. So we'll call it, we compared A to A, B to B. So then we go out to look at C, and then this C is connected to another carbon, and the highest atom this one has is a hydrogen. So we're going to say this group in the ring is 1. This one is 2, this one is 3, and the hydrogen is 4. So it looks like it's going clockwise, and the hydrogen is in the back, so it is what it is. It's going to be R. And over on the other one, it goes 1, 2, 3, and then the hydrogen's in the front. So it looks R, but since the hydrogen's in the front, we have to switch it. It will be S. So since those are opposite of each other, they are enantiomers. Letter J, I would say the easiest thing to do is think about turning that molecule on the right like a steering wheel. So let's turn it 2 positions for each group. So we're going to move the methyl 2 positions this way, which means that the bromine is going to move 2 positions this way. Just like in S, we're moving everything counterclockwise. So in comparing these two visually, hopefully we can see that they are the opposite. They are what they look like when they look in the mirror, which would mean they should be enantiomers. And if that doesn't make sense, let's just determine R or S to make sure. So bromine is 1, this group is 2, this is 3, and the hydrogen's in the back, it's 4. So it's going clockwise, and it is what it is because the hydrogen's in the back. And then on the other chiral center, this group is 1, this is 2, this is 3, and the hydrogen is in the front. It is 4. So 1 to 2 to 3, it looks S, but the hydrogen's in the front, it's going to be R. And then on the other molecule over here, let's start with the bromine. So bromine is 1, the group in the middle is 2, this is 3, hydrogen's in the back, it's 4. So 1 to 2 to 3, it's going counterclockwise, and the hydrogen's in the back, so it is what it is. It is S. And then the other chiral center, this is 1, 2, 3, and the hydrogen is in the front. It is 4. So it looks like it's going to be R, but since the hydrogen's in the front, we have to switch it. It will be S. So this molecule is RR, and this one is SS. So they are complete opposites of each other, making them enantiomers. All right, for problem number 3, we are going to determine whether each of these chiral centers is R or S. So while we're doing this, I'm going to go over a few things that maybe you didn't pick up on while you filled out the workbook, just to make sure that we answer all those questions that seem to be common. So for letter A, remember that to determine the chirality of each chiral center, we need to look at the atomic number of the atoms. So the higher atomic number the atom is, the higher priority it is. So if you don't already, I would pull out a periodic table. So in this case, bromine is 1, and then we have to think about group 2 and 3. So this will be group 2 because it's a carbon attached to another carbon, while this is a carbon attached to a hydrogen. So this is 2, this is 3, and then the last group is a hydrogen. So a lot of times my students ask, well, where is the hydrogen located? So when you have a perspective formula, you should always have 2 straight lines. So in this case, our 2 straight lines look like this. You should have what we call a wedge. So that's where our bromine is. And then the last line is always a dash. So a common student question my students ask is, does it matter where the dash goes? So as we look at this, you could say, well, the hydrogen could be here, the hydrogen could be here, or the hydrogen could be here. So out of the 3 of those, the only one that is not allowed is this hydrogen on the bottom. So the hydrogen, the dash and the wedge lines always have to be close to each other. They always have to be friends. So it doesn't matter, again, if you put the hydrogen on the back here or here, but you always have to keep them next to each other. We'll just erase this one. Again, it doesn't matter either way. So that is group 4. So now we figure out R or S. So we draw the shortest line between 1 and 2. So it looks like we're going clockwise, and the hydrogen's in the back, so our answer is what it is. It is going to be R. This one over here, the group that's missing is a hydrogen, and it's going to be in the back. So again, it just has to be friends with the wedged line. And so let's look at the priority of our group. So we'd first consider this one versus this one versus this one. So we have carbon versus carbon versus carbon versus hydrogen. So hydrogen instantly loses. It's 4. This carbon is attached to another carbon. So if we go out one further to compare, this carbon here, this one on the right side, behaves as if it's attached to 2 carbons because of that double bond. So when we say carbon versus carbon versus carbon, the carbon on the right acts like it's bound to 2 carbons. The carbon down here is bound to essentially a hydrogen, and this carbon is attached to another carbon. So the order is going to go, this is group 1 because it's attached to 2 carbons, this is 2, and this is 3. So we're going to draw the shortest line to connect them, 1 to 2 to 3. It's going counterclockwise, and the lowest priority group is in the back, so it is what it is. This will be S. Letter C is something we call a Fisher projection. So we have 2 types of structures, perspective and Fisher. So Fisher means that the things that are on the horizontal here are coming out towards you. I think of it as giving you a hug. That's those two arms of someone coming out. They are in the front. So if the group is in the front, you'll always have to switch your answer. So as we compare the priorities of this groups, we say this is a carbon attached to 2 carbons. This is attached to 1 carbon. This is attached to no carbons. So our priority goes 1, 2, 3, 4. So to connect those lines, we're going to go in the counterclockwise fashion. And since the hydrogen's in the front, we have to switch our answer. So even though it looks S, the answer is going to be R. Letter D, here is our chiral center. So let's look at the priorities of those groups. This is a carbon attached to no carbons. This is a carbon attached to 1 carbon. And this is a carbon attached to 1 carbon. So we know that the highest priority group is either going to be this one or this one. So we go out one further. This is a carbon attached to another carbon, and this is a carbon attached to 1, 2, 3. So our highest priority group is going to be this one, followed by this one, and then this one, and then our hydrogen is in the back. It's friends with the wedged line. So we go 1 to 2 to 3. It's going clockwise, and the lowest priority group is in the back, so it is what it is. It's going to be R. Letter E. As we look at our chiral center, we'd say we have a carbon attached to no carbons, a carbon attached to 1 carbon, and a carbon attached to 1 carbon. So then we go one further. This carbon is attached to none, and this carbon is attached to 1 more. So our highest priority group is here. This is group 2, this is group 3, and hydrogen is in the back. It's 4. So 1 to 2 to 3, it's going counterclockwise, and the hydrogen is in the back, so it is what it is. This is going to be S. Letter F. So this carbon behaves as if it's attached to 2 carbons because of the double bond. This carbon is attached to 1. This one's attached to 0. So our priority is going to go 1, 2, 3, and then our low priority group is in the plane. So because the low priority group is in the plane, the general process is that you switch it with whatever group is in the back. So in this case, 3 is in the back. So this will be 4, and this will become 3. So then we determine the answer. Going the wrong way here. So 1 to 2 to 3, it's going clockwise. But since we switched 2 groups, we have to switch our answer. So although it looks like it's going to be R, it's going to actually be S. So just to reiterate that, if the low priority group is on the plane, you switch it with whatever group is in the back. And then you find your answer and you switch it. All right, letter G. We have another Fisher projection. OH is 1, NH2 is 2, methyl is 3, and hydrogen is 4. So remember on the Fisher projection, the things that are on the horizontal are in the front. So in this case, the lowest priority group is already in the back. So our answer is what it is. 1 to 2 to 3, we're going counterclockwise. This is going to be S. Letter H, here's our chiral center. Bromine is 1, this group is 2, this group is 3, and the hydrogen is on the plane. It's 4. So again, when the lowest priority group is in the plane, you're going to switch it to put it in the back, and then you'll switch whatever answer you come up with. So in this case, 1 to 2 to 3, it looks like it's going clockwise, which would be R, but since we switched 2 groups, we have to switch our answer. It should be S. Letter I. The OH is 1, and then we had to compare all these carbons. This is a carbon attached to 2 carbons. This is a carbon attached to 1 carbon. And this is a carbon attached to none. So it's going to go 2, 3, 4. So our low priority group is in the plane. So we're going to cross it off and switch it with whichever group is in the back. At this point, I'm realizing all 3 examples we've done so far has been a switch of 3 and 4, but that is just coincidence. It could be 1 or 2. It's just a random thing that they've always been 3 or 4 at this point. And then we're going to switch our answer. So our answer goes 1 to 2 to 3. It's going counterclockwise, which would be S. But we have to switch our answer because we switched 2 groups. It is going to be R. All right, moving on to letter J. So here is our chiral center. This is a carbon that acts as if it's bound to 2 carbons. This is bound to none, and this is bound to 1. So it goes 1, 2, 3, and hydrogen is 4. So our lowest priority group is on the plane. So we're going to switch it to put it in the back. So here to here, we just switch those 2 groups. And then it goes 1 to 2 to 3. It looks like it's R, but since we switched 2 groups, we have to switch our answer. It should be S. Letter K. We have a carbon attached to 2 carbons, a carbon attached to 1 carbon, a carbon attached to 1 carbon, and a carbon attached to 1 carbon. So this is going to be group 1. This is a common confusion on this problem. That one's 1 because it's attached to 2 carbons. So then we go out 1 further. This one is attached to a hydrogen. This one is attached to a carbon. And this one is attached to a carbon with 2 carbons. So this will be group 2. This is group 3. This is group 4. So our low priority group is in the front. So we're just going to switch whatever answer we come up with. So it goes 1 to 2 to 3. It looks S, but we have to switch it since the low priority group is in the front. It will be R. And then on this last one, L, it is a Fisher projection. So NH2 is going to be 1. We treat this group as if it's bound to 2 carbons. We treat this group as if it's bound to 3 carbons, and this group is bound to no others. So it'll be 2, 3, 4. So our low priority group is in the front here. So we're going to switch whatever answer we come up with. It goes 1 to 2 to 3. It looks like it's R, but we have to switch it. It will be S. All right, for letter M, here's our chiral center. So this carbon is a carbon attached to 3 carbons. This one's a carbon basically attached to 2, and this one is attached to 1. So this is group 1, this is 2, this is 3, and the hydrogen is in the back. It is 4. So 1 to 2 to 3, it looks like it's going to be R, and since the hydrogen's in the back, it is. Letter N is a Fisher projection. So bromine is 1, NH2 is 2, this group is 3, and our lowest priority group is the hydrogen. Remember, with the Fisher projection, if it's on the horizontal, it's in the front. If it's on the vertical, it's in the back. So in this case, our low priority group is in the back, so our answer is what it is. It's going counterclockwise. It should be S. Letter O is also a Fisher projection. So chlorine is 1, OH is 2, NH2 is 3, and methyl is 4. So since our low priority group is in the front, we're going to have to switch our answer. So 1 to 2 to 3, it's going counterclockwise. It should be S, but since the low priority group is in the front, we switch it. It will be R. Letter P, we again have a Fisher projection. OH is 1, the ethyl group is 2, methyl is 3, and the low priority group is the hydrogen. It's 4. So since the low priority group is on the horizontal, we're going to switch our answer. It goes 1 to 2 to 3. It looks like it's going to be R, but we switch it. Since it's the low priority group's in the front, it will be S. Letter Q is kind of tricky. We would say that this is a carbon that behaves like it's attached to 2 carbons. This is a carbon that's only attached to 1, and this one is attached to none. So we'd say 1, 2, 3, and then hydrogen is in the back. It is 4. So 1 to 2 to 3, it's going clockwise. And since the low priority group is in the back, it is what it is. It's going to be R. Letter R, group 1 is our NH2, then our ethyl, then our methyl, and then our low priority group is a hydrogen on the plane. Finally, an example where the group on the plane is not being switched with group number 3. So we're going to switch the low priority group with the group that's in the back. So in this case, we're switching 1 and 4. So it's going 1 to 2 to 3. It looks like it's going clockwise, but we have to switch it. Since we switched 2 groups, it will be S. Letter S. Here is our chiral center. So we have a CH2 versus a CH2 versus a methyl. We go out one further. This is a carbon attached to 2. This is a carbon attached to 1. So it goes 1, 2, 3, and then the hydrogen is in the front. It is 4. So 1 to 2 to 3, it's going counterclockwise, but we have to switch it since our low priority group is in the front. It is going to be R. Letter T, we have a carbon here attached to 3 carbons. This is a carbon that behaves as if it's attached to 2. This is attached to 1, and this one is attached to none, just a hydrogen. So it goes 1, 2, 3, 4. So we go 1 to 2 to 3. It's going counterclockwise, but our low priority group is in the front. So we have to switch our answer. Answer looks like it's S, but we switch it, therefore it's R. Letter U, OH is 1. This group is attached to 2 carbons is how it behaves, so that's 2. This is attached to 1, it's 3, and this is attached to none, it's 4. So since our low priority group is in the plane, we're going to switch it to put it in the back. So we're switching groups 3 and 4 in this case. So 1 to 2 to 3, it's going counterclockwise, but since we switched 2 groups, we have to switch our answer. It will therefore be R. All right, last row. So here's our chiral center. Highest atomic number is bromine, then chlorine, then we have a propyl versus a methyl. So our low priority group is in the plane, so we're going to switch it to put it in the back. So 4 becomes here, 2 becomes here. So it goes 1 to 2 to 3. It looks like it'll be S, but since we switched 2 groups, we have to switch our answer. It will be R. Letter W. This is a group that behaves as if it's attached to 3 carbons, and so is this one. And then we'd say, okay, well, this one is attached to another carbon, and this one is not. So this will be group 1, this will be 2, this will be 3, and then the hydrogen is in the back. It is 4. So 1 to 2 to 3, it's going clockwise, and it is what it is because the low priority group is in the back. So it's going to be R. And last one, letter X. Here is our chiral center. This carbon is attached to 2 carbons. This carbon's attached to 1, and so is this one. And then this one also is attached to another one. So that's why it's 2. This is 3, and the hydrogen is in the front. It's 4. So 1 to 2 to 3, it's going clockwise, but since the low priority group is in the front, we have to switch it. It will be S. All right. On this page, we are going to draw the enantiomer in both diastereomers for the compound. And as it says, if there's not an enantiomer or diastereomer, write none. So the main thing we're looking for in this problem is we're looking to, I'm mainly wanting you to recognize if there is a meso compound in the group of stereoisomers, and if so, then I need you to recognize that meso compounds do not have a mirror image. Structure A, the first thing we're going to do is draw the enantiomer. And so there are essentially two very common ways my students use to do this. The first is just to draw what molecule A sees when it looks into the mirror. So if you wanted to classically draw what molecule A sees when it looks in the mirror, this is the mirror image that it would see. Alternatively, the other way my students like to do this is just to switch the chirality at each center. So this would stay as bromine, but instead of up, it goes to back, and the same with the chlorine. So these two molecules, just to make that connection, they are identical to each other. It's just two different ways to do the same type of problem. For a diastereomer, you are going to keep one site the same and then switch the other site. So for example, here we keep the bromine the same, and then we're going to invert the chlorine. So remember, a diastereomer has one chiral center that is identical. So here is our identical chiral center. And then one chiral center that is opposite. So then to draw the last diastereomer, you can just draw what that enantiomer looks like of structure C. So that's one choice, like this. So again, that's what it looks like when it looks in the mirror. Or you can just invert both of the stereocenters from molecule C. So again, these are identical. Just to give you the full story here, you could also have drawn the opposite. You could have drawn where bromine is inverted and then chlorine stays the same. And basically, as you can see here, it would be the same as this one. And then when you draw the mirror image of it, you would draw what we drew here. So all I really want you to do is be able to draw all the stereoisomers that there are for a molecule. So it asks, how many different stereoisomers are there? So as long as there's no meso compounds, you're always going to have 4 if there's 2 chiral centers. Remember that formula is 2 to the n, where n is the number of chiral centers. And so again, none of these are meso because there's no plane of symmetry. So as it says, which of the above molecules do not rotate light? It's basically asking which of the above molecules are meso, and none of them are. So all of the molecules rotate light in this case. Rotate light. So moving on to B, we have this molecule that has 2 methyls. So to draw the enantiomer, we're going to draw what this molecule sees when it looks into the mirror, which is this. Again, you could draw where you invert the stereochemistry at each site. I don't want to confuse you guys, so if you're ever questioning whether your molecules are valid or you did it correctly and you're unsure, just email me, or we can find a time to meet and discuss. To draw the diastereomer of compound A, we just need to invert the stereocenter at one chiral center. So both of the methyls could be up, or both of the methyls could be down. And then when you draw the enantiomer of structure C, you're going to find that it is identical to structure C. So there is not another stereoisomer for this compound because structure C is a meso molecule. It has a plane of symmetry down the middle. So we ask, how many different stereoisomers are there for structure A? So remember, at the max, it's 2 to the n, where n is the number of chiral centers. So 2 to the 2 in this case would be 4. But we have one that does not exist because it's meso. So in this case, there are only 3 stereoisomers for this particular molecule. And then it asks, which of the above molecules do not rotate light? So in this case, structure C does not, because it is meso. Letter C, we are just doing the same thing we did on the previous page. So for the enantiomer of structure A, we are going to draw what this molecule sees when it looks in the mirror. Again, there's more than one way to write this answer, but we'll make it easy and draw what it sees when it looks in the mirror. To draw the diastereomer, you invert the stereochemistry at one chiral center and keep the other one the same. So this is one option. And then to draw the other diastereomer, you're just going to draw the enantiomer of structure C. So in this case, this is what structure C when it looks in the mirror. So as we look at those four molecules, we hopefully recognize that none of them have a meso. None of them are meso because there's two different chiral centers. So there's not a possible plane of symmetry. So when it asks how many different stereoisomers there are, it is the maximum number for two chiral centers, which in this case is 4. And then it asks which of the above molecules do not rotate light, and all of them rotate light because all of them are chiral. We have no meso molecules. All right, letter D. We're just continuing on. We're doing the same thing we did before. So for structure B, we're going to draw the enantiomer of A. So when A looks in the mirror, this is what A sees. And then we're going to draw the diastereomer of A by inverting the stereochemistry at one site. And keeping it the same at the other. And then to get the last diastereomer, we're going to draw the enantiomer of structure C. So that would give us these four compounds. Hopefully at this point you realize that there's no way this molecule does not have one of those pairs being a meso molecule. So to figure out which one is meso, let's just label them R or S. So this first one goes 1, 2, 3, and hydrogen is in the back. It's 4. So this one is going to be R. And then the other side, 1, 2, 3, hydrogen is in the back. This one's also going to be R, which means that these two should be S. And so structure C is likely going to be meso, which means structure D does not exist. So let's confirm that. 1, 2, 3, and hydrogen's in the back. This is going to be R. And then 1, 2, 3, but hydrogen is in the front. It looks R, but we have to switch it. It's S. So we have two chiral centers with the same groups attached. We have a plane of symmetry down the middle, and one side is R and one side is S. So that means that this molecule does not exist. So there is not a fourth stereoisomer. So when we're asked how many different stereoisomers are there are only 3 because we have a meso compound. And then it asks which of the above molecules do not rotate light, and that would be structure C because it is meso, which means that it is not chiral. It does not have a mirror image. That is the opposite. All right, for question 5, I want you to compare a large subset of molecules and determine how they are related. I do believe that the fastest way, I will teach you the fastest way to do this, and I think the fastest way involves making a table to compare them. So I would just put the two chiral centers at the top, and then the structures A, B, C, D, E on the side. And then I'm going to quickly show you how to label R or S to each of these. So for the first one here, it goes 1, 2, 3, and the hydrogen is in the front, which is 4. So it goes 1 to 2 to 3 counterclockwise. It looks like S, but since the hydrogen's in the front, it's R. So then going through all of these, structure B has the hydrogen and the OH switched. So anytime you switch two groups, you switch the chirality. Structure C has the same as B. Structure D is the same as A, so it's going to be R. And then structure E, the easiest thing to do in my mind is to take this like a piece of paper and then turn it like a steering wheel. So don't flip it over, just turn it around. So when you turn it, it should look like this. So when you compare structure A and structure E, they are the same at that site. So we've already figured out the chirality at 5 out of 10 with only determining 1. So let's do this side. 1, 2, 3, and hydrogen is in the front. It's 4. It looks like R, but since the hydrogen's in the front, it is S. So then over here, the hydrogen and the OH are switched in B, so that would be R. This one is the same as A, so it'd be S. This one is the same as B, so it'll be R. And then this one here is the same as A, so it would be S. So now we're asking, which of the above structures are identical to A? So we'll kind of highlight them to cross them off. So A is RS. That's what we're going to compare everything to. So which ones are identical? Upon first glance, we should for sure see that E is identical. And then the other thing that we hopefully will notice is that B is also identical. You might be asking yourself, why is B identical when they're reversed? We have 2 chiral centers with a plane of symmetry. Both of our groups have the same thing. So A is a meso compound. So RS versus SR is the same. So which of the molecules are identical to A? It's B and E. The next question asks, which are diastereomers? So as we look, structure C is the same on the S side as it is to A, but it's opposite on this side. So that would make it a diastereomer. So C is a diastereomer. And then also D. So these are the same in D, and then they're opposite here. So C and D are diastereomers of A. And then the question asks, which ones are identical to A? So since in enantiomers of A, and since A is a meso molecule, it's achiral, and there are none. So there is none are enantiomers. Then it asks, how many stereoisomers are there? So this is kind of similar to our previous problem. There's only 3 because there's a pair of meso compounds which are identical. And then it asks, which of the above molecules do not rotate light? So anything that's meso does not rotate light. So that would be A and B and E. All right. Problem B, we're just doing the same thing over. So we have 2 chiral centers. This molecule has, again, 2 chiral centers with the same groups. So be on the lookout for a meso molecule. So let's figure out R or S quickly. So 1, 2, 3, hydrogen is in the back. So it looks like it's going to be R, and it is because the low priority group is in the back. Structure B has the same chirality. It will be R. Structure C is the opposite. It will be S. Structure D is the same as C. It should be S. And then structure E, we're going to turn it like a steering wheel. We're not going to flip it over. We're just going to turn it, which will yield this. And so it's the same as A. So it's R. So we figured out 5 of 10. Now let's do this one. 1, 2, 3. Hydrogen is in the front. So it looks like it's going to be S, but since the hydrogen's in the front, it's R. Then structure B, it's inverted. So whatever it was, it's going to be the opposite. So it should be S. Structure C is the same as B, so it should be S. Structure D is the same as A. It will be R. And then structure E is the same as A. It will also be R. So which of the above molecules are identical to A? So A is RR. So the only one that's identical as we look at this list is E, which is also RR. So E is identical. Then it asks which of them are diastereomers. So that means they're the same at one site and the opposite at the other. So B is definitely a diastereomer. Again, I'm just highlighting them because once we use them as a relationship, we won't use them again. Which of them are diastereomers? So then we also should look. So C goes opposite, opposite. So since they're both opposite, it's not a diastereomer. A is opposite with D on one, and then it's the same on the other. So B and D are going to be our diastereomers. And then which of the above molecules are enantiomers, which means complete opposites. And so since A is RR and C is SS, C is going to be our enantiomer. It asks, how many stereoisomers are there for structure A? So again, there is one meso compound, like this is a meso compound. And so there's only if you have a meso compound, the maximum stereoisomers you can have is 3. And which of the above do not rotate light, which is basically asking which of the above are meso. So mesos are RS, so we have B and D. All right, continuing on for this problem, we're just going to keep doing the same thing. This is a molecule that has 2 different chiral centers, so you have to make sure that we're specifically looking at the chiral center attached to the chlorine, and then specifically looking at the chiral center attached to the bromine. So let's figure out this first one. It goes 1, 2, 3, and hydrogen is in the front. It's 4. So it goes 1 to 2 to 3. It looks R, but since the hydrogen's in the front, it's going to be S. So now let's try to figure out the rest. So between A and B, we switched 2 groups. So anytime you switch 2 groups, you switch your answer. So this one's going to be R. This one does not look the same. So we're going to just figure that one out on its own. 1, 2, 3, hydrogen's in the front. It's 4. So 1 to 2 to 3. It looks S, but we have to switch it since the hydrogen's in the front. It's R. This one also does not look the same. So 1, 2, 3. Hydrogen is in the front. So it looks R, but the hydrogen's in the front, so we switch it. It's S. And again, this one doesn't look the same as any of them. So 1, 2, 3. This one's going to be S as well. All right, going back to the bromines. Bromine goes 1, 2, 3. Hydrogen's in the back. It's 4. It's going clockwise. It will be R. This bromine in structure B is the same as A, so it will also be R. This bromine does not look the same as A or B, so we'll figure it out on its own. It goes 1, 2, 3, and hydrogen is in the back. It's 4. It is what it is. Since the hydrogen's in the back, it's going to be S. This bromine here, 1, 2, 3, hydrogen's in the front. It's 4. 1 to 2 to 3. It looks R, but we had to switch it since the hydrogen's in the front. It's going to be S. And then 1, 2, 3, hydrogen's in the front. It looks like it will be S, but since the hydrogen's in the front, we have to switch it. It's R. So our first question asks, which of the above molecules are identical to structure A? So structure A is SR. So we are specifically looking for chlorine S, bromine R. So the only one that's identical is structure E. Then it asks, which of the above are diastereomers? So it means same at one site, opposite at the other. So B is a diastereomer. This one's opposite, opposite, so that is not. This one's same and then opposite. So B and D are both going to be diastereomers of structure A. And then the last question asks, which of them are enantiomers? So structure C is the complete opposite. It is going to be the enantiomer. The next question asks, how many stereoisomers are there? So none of these are meso because we don't have the same groups attached to our chiral center. So we have 2 chiral centers, no plane of symmetry. It's going to be 4. And then it asks, which of the above molecules do not rotate light? And all of them rotate light because they are all chiral. We have no meso molecules. Last problem. So we'll just do the same thing we did before. We have 2 CH3 groups. Hopefully just looking at this, we know that there's going to be meso molecules. Hopefully by even looking at those molecules, you can recognize that they may be meso. Let's figure out RS and then kind of just use that to go through all of them. So 1, 2, 3. Hydrogen is in the back. It's 4. So this one is what it is. It's going to be R. So this one is R. Structure B is opposite at that site. So it will be S. Structure C is not lined up perfectly the same. So let's just figure out, there's a couple ways you could do it. I would say just figure out whether it's R or S. Let's start here and go 1, 2, 3. Hydrogen is in the back. It is 4. So this one's going to be R. This one is the same as structure B, so it's going to be S. And this one is the same as structure A. It's going to be R. Let's look at the second chiral center here. So 1, 2, 3. Hydrogen's in the front. So it looks to be S, but since the hydrogen's in the front, we have to switch it. It will be R. Structure B is inverted. The hydrogen and the CH3 are switched, so that switches our answer. If A was R, then B is S. Structure C is not as obvious, so let's just figure it out. 1, 2, 3, and hydrogen's in the front. So it looks like it's S, but since the hydrogen's in the front, we switch it. It will be R. Structure D is the same as A for that center, so it's R. And then structure E is the same as B, so it's S. So we're asked, which of the following molecules are identical to A? So A is RR, so the only other RR we have here is C. Which of the above is diastereomers of A? So that means one site the same, one site opposite. So D has R for the second CH3 and S, so they're the same at the RR and opposite here. And E is the same. We have same here and then opposite here. So D and E are diastereomers. And then which one is an enantiomer of A? So that would be structure B. A is RR and B is SS. So then it asks, how many stereoisomers are there for structure A? So as we said, you can see that structure D and structure E are meso compounds. So if there's a meso compound, you're only going to have a maximum of 3 possible stereoisomers for any molecule with 2 chiral centers. And then it asks, which of the above molecules do not rotate light? So you're looking for anything with the RS, which in this case is D and